Hey there, statisticians. Mr. Hayes, we're back. We're going through sampling distributions. I'm using the StatsMedic curriculum. Their link is down below. My link to my copy of the notes is down below. You can leave a like down below, a comment down below, subscribe down below, everything you could possibly want. Wow, I started sounding way too much fun there. With a lot of what we do second semester involves food. This is one of them. We're going to talk about Reese's Pieces. Specifically, if you take a sample of Reese's Pieces, how many of them would be orange? And so you're like, well, how hard could that be? Well, if we're going to need to be systematic, it gets a little bit more complicated. So in this case here, specifically, we're going to say we had 1,000 Reese's Pieces in a giant bag and you pulled 50 of them. How many of those would be orange? Now, obviously, you don't want me touching them to count the 1,000. You probably don't want to take 50 and then put them back because somebody else will touch them, et cetera, et cetera. So what do? We're going to do an applet for this. But before we get to that, we're going to talk about what type of probability distribution that this has. Now, this is going to turn out to be binomial. Why? Because it does have a success and failure. We do have a fixed number. And so just to double check, there's our bin category. So we have success, failure. Success is an orange. Failure is not orange. There is no replacement, which is usually a problem. However, remember, we've got a little 10% rule. So 50, the number that we're taking, is less than 1/10 of the 1,000 that we're taking it from. N is fixed at 50, and then my probability is also fixed at 40%, because we're going to take the Hershey's company that owns the Reese's brand at its word. So now what you're going to end up doing is that there's an applet. Again, the link there is down below, and we need to change a couple of things. Oops, wrong side. So probability of orange is 40%. We're going to take 50 of these. Now, if you leave animate on, you're going to do this a total of 5 times. Report your data in. So when you draw your samples, the animation shows you actually pulling out one candy at a time. It's really cute. Actually, it is kind of fun. And so in this case, we got 16 of them. Oh, no, that's those are rows of 6. So that is 19 of them. Boom, it puts it down. Every time you take an additional sample, it's going to make the dot plot for you. Now, I've got 24 students in my class this year, plus me, because, hey, who doesn't like candy? So we need to add an additional 124, because 5 times 25 is 125. But I'm going to turn off animate because nobody's got time for that. So I'm going to go ahead and hit that. And draw samples. And draw samples. Hello. There we go. So there's all, it goes through and simulates 125. So we have as low of about 8 all the way up to about 29. And we have everything in between. Okay. And that is what would go here in your notes. So you would have your 5 up here for number 2, and then the values of the stickers, you put the values on the stickers, stick them up, et cetera, et cetera. Now, like with every dot plot that we're doing, what do each one of those dots on this? Why does that keep popping up? Fun fact, I didn't know. You press F3 in Google Chrome and you get the find bar. So each one of these dots here represents a sample of 50 Reese's Pieces that have been taken and the number of oranges in them. And so that is what we're going to put down here for the answer for number 4. Okay. Now, like we were talking about in section 1, when we start talking about means, the means, remember, are basically, if you're talking about the population mean, okay, you can go ahead and just take, so the mean of the population is going to be the number of candies that you take of 50, and you're going to multiply by your proportion, and you get an answer of 20. And likewise for your standard deviation over here, you end up saying, okay, 50 times P times not P, and then you're going to take the square root of that. And so that turns out to be 3.46. Okay, couple of other things. And some of you might be saying, Mr. Hayes, we're not doing the proportions yet. We're going to get there. Okay, because remember, for proportions, we just need to take these numbers and divide it through by 50, which we'll get to in page 2. All right. So now in terms of the approximate shape of the sampling distribution, while we come back here, it looks approximately normal, which is great because, that makes our lives a little bit easier. We can also use the normal curve here because of large counts. Because remember, if you have a sample, and as long as you can guarantee, well, not guarantee, but, the average number of successes and failures are each bigger than 10, then you can go ahead and say it's approximately normal. We can put our our mean down here, and then we can put our basis for our normality up there. All right. So again, like you guys were saying, you people are saying, how does this work with proportions? Well, you're going to go back to those 5 samples that you took, and you're going to turn them into a proportion. And you just do that by dividing through by n. So you're going to turn the number of blah, 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 blah. So on the sample, write the proportions below, put the dot plot on the board. So you're going to go through and you're going to take each of the samples from the first page. So like I had a 1 of 21. I'm going to divide that by 50. I get 0.42. If I had 27, I would divide that by 40 and get 0.54. If I was down at the 12, I'd divide it by 50. I'm sorry, it should be divided by 50. And I'm going to get 0.24. And you're going to draw that. Now, some of you may already be thinking, hey, didn't we learn back a couple chapters ago that if we multiply a distribution by a constant that the shape's going to stay the same? And the answer is perfectly yes. Your shape is going to be the exact same thing as we have here. The only thing that's going to change, in fact, the numbers and the heights are going to be the same. The only thing is that all of these values down here will be divided by 50. So this will start down here at a low value of 0.12 all the way up to 0.6, or as we used to say, 60, as we used to say, 60 hundredths or 6 tenths. Wow. Anyway, so what's the next question? So sketch the dot plot. What does each dot represent? Each dot represents a sample of 50 Reese's Pieces and the proportion of which are orange. Okay. So again, the shift has changed a little bit in terms of what the dot plot means. So instead of meaning the number of orange candies, it's the proportion of orange candies. Now, for the new mean and the new standard deviation, this is where some of the fun is starting to happen, people. So what's going to happen here is this. We're just going to take our mean and our standard deviation and divide it by 50. Why? Because that's what you do. You're just changing it. So like here, if the average is normally 20, that means that 20 out of the 50 are going to be orange, which just means you're going to divide it out, and that means we get a 40%. That's exactly what we had before. It's amazing. I know. Glad you saw it. For the other one, remember, everything was varying by 3.46 orange candies, right? Typically varies, I should say. So since we're talking about the number of orange candies that things are going apart by, we're going to divide that by 50 as well, and we're going to now get a standard deviation of 0.0692. 692 10,000ths. So the shape, has it changed? No. So that means it's going to be approximately normal because the first one was approximately normal. The only thing that is changing is both our mean and our standard deviation for that. Which, if you think about it, if we're talking about proportions and actual numbers, it shouldn't change. I mean, it's going to be basically the same thing. The data hasn't changed. We're just, how we're representing it has changed. So now here's a big question. So, and this is similar to what we've already been doing. We know that a bag of Reese's Pieces contained 40% that are orange. So if we select a random number of 50 candies, what's the probability that that sample proportion will be 50% or greater? So we're going to go through, and since it's approximately normal, we can go through and say, all right, we want it to be bigger than 50%. So we've got our curve. Yes, you have to draw it. Why? Because it shows knowledge. Sorry, just making sure I'm not missing anything. So then over here, since we've got a normal curve, that means we can start using our z-scores. So we've got what would be normally x minus x bar. In this case, we're going to use the proportion minus our known proportion, so p hat, divided by the standard deviation. So again, if we're going to do this in terms of normal thing, in terms of a standard formula, so what do we say? We said the p that we're expecting minus our p hat divided by our standard deviation. Now to get that, remember what we ended up doing was we took p minus 1 minus p, oops, I forgot the n. No, I didn't. Oh, check this out. This is spiffy. So what we ended up doing was this, right? We had, this was our original standard deviation divided by n, right? So we can simplify that a little bit because if we extend the square root, this now becomes n squared because we moved it on the inside, right? Well, if we move it on the inside, is that coming out okay? Let me move it and see if that works a little bit better. The glare from the wet ink is kind of throwing it a little bit. But now if we do that, one of the ends are going to go away, so it simplifies out. So this is actually going to turn into P times 1 minus P all over N. And then we're just going to keep this up on top. Okay? So that's how that formula comes to be. I know some of you care, some of you don't. If you don't care, just forget about it. So anyway, so we end up coming up with a z-score of 1.45 regardless. So now that 1.45, remember this number right here is right here. That's my z-score. So the area that goes from the left-hand side all the way up to there is 9.26 or 92.65%. So 0.9265. So if we're using table A, we just have to subtract that from 1. If you ended up using normal CDF, then you're going to go normal CDF, and then you would say, okay, I'm going to go from 1.45. Yes, use the z-score. So 1.45 to 10,000, and then we're going to use, what's our mean? 0.1, right? So again, label this out. This is lower, this is upper, this is my mean, this is my standard deviation. Okay, but regardless, that means that we have a 0.0735 probability that we're going to get 50% or more oranges in our bag of Skittles. And the benefit of using this, obviously, that is if we're going to be 50, 50 candies or bigger. The benefit of using proportions is that it transfers a little bit better. It's not perfectly clean because, N changes, but it does make it a little bit easier there. So anyway, a little bit longer video than usual, but I think it hopefully laid out a little bit nicer, even in spite of myself. The link for part 2, the formalize, is down below. So I hope I'll see you there. If you have any questions, please let me know. See you soon.